Dear students, in the last class, we have studied about the inorganic polymers, especially the silicon polymers. So, today, let us study the other class of inorganic polymers known as phosphazenes, or these are also called the phosphonitrile compounds. Before to know about this, just we have a glance of the inorganic polymers. So the inorganic polymers, their main chain element is organized basically in a third to sixth group elements, especially boron, silicon, phosphorus, germanium and sulfur. These inorganic polymers, they have low temperature flexibility, high thermal and oxidative stability, flame retardancy, novel forms of chemical reactivity. In this type, we have studied the silicon polymers. And today, let us take the another class of polymers known as phosphazenes, or they are also called phosphonitrile compounds. Phosphazenes or phosphonitrile compounds are the inorganic polymers containing alternate phosphorus and nitrogen atoms with two substituent on each phosphorus atom. Their structural formula is N double bond P, and the phosphorus is having the two R groups, and here the nitrogen valency is 3 and phosphorus valency is 5. And here the R may be alkyl, aryl or even the halogen groups. Each macromolecule may contain about 15,000 or more repeating units with the molecular weight in the range of 2 million to 10 millions. We have two types of phosphazenes. One is linear phosphazene and another one is cyclic phosphazenes. Linear phosphazenes have N double bond P, the chain in N numbers. Cyclic polymers, they are in the form of cycle. It may be a trimer, it may be a tetramer, pentamer, hexamer and so on. Instead of alkyl or aryl group, if chloro group is introduced in the phosphazenes, these compounds are called phosphonitrile chlorides. These phosphonitrile chlorides have more significant characters or the properties than the alkyl or aryl groups. Phosphonitrile chlorides are also either linear type or a cyclic type. Here instead of R, they are replaced by the Cl atom. The phosphonitrile chlorides are white crystalline solids obtained by heating phosphorus pentachloride with ammonia with the elimination of hydrogen chloride. So PCl5, when it is treated with ammonia, we get cyclic trimer of the polymer and also the linear, the phosphazene polymers. The solid phosphonitrile chloride on heating transformed into elastomeric material known as inorganic rubbers. Instead of ammonia, ammonium chloride in chlorobenzene or tetrachloroethane solvent at 120 to 140 degrees centigrade can also be used in the manufacture of phosphonitrile chlorides. Other methods of preparation of polyhalo phosphazenes are as follows. The first method, just by heating P3N5 N, that is a N number of this, a polymer in chlorine at 700 degrees centigrade, we get phosphonitrile chlorides and other products. Another method is a chlorofluoropolymer, that is PnFCl4. It's a tetramer, is prepared by heating a trimer PnCl2 thrice with lead fluoride. The reaction is given. The trimer phosphonitrile chloride can also be prepared by treating S4N4, that is tetrasulfur tetranitride, with thionyl chloride in phosphorus trichloride. This reaction is very important reaction. S4N4 plus 6SOCl2 plus 12 PCl3 gives the 4 PnCl2 thrice plus 10S plus 3O2 plus 12 Cl2. It's a very peculiar reaction. Students, you have to remember this balanced equation. Cyclic trimer, that is NpCl2 thrice, has melting point 114 degrees centigrade and boiling point 256 degrees centigrade at 1 atmospheric pressure. It is readily soluble in ether, benzene and carbon tetrachloride. Tetramer NpCl2 4 times has melting point 123.5 degrees centigrade and boiling point 328.5 degrees centigrade at 1 atmospheric pressure. It has lower solubility in ether, benzene and carbon tetrachloride. When the solutions are allowed to stand for long period, the polymers get cross-linked and slowly gel formation takes place. On heating to 150 to 300 degrees centigrade, that is the trichloro, the cyclic polymer, both trimer and tetramer polymerize to an elastomeric product with the high molecular weight of the order of 20,000. On further heating to 300 degrees centigrade, this product gets depolymerized. Now, the trimer, the phosphonitrile chloride, can undergo substitution reaction. So when we take a trimer NpCl2 thrice with the sodium fluoride, the Cl are replaced by fluorine, we get the difluoro, the phosphonitrile the fluoride trimer. And when phosphonitrile chloride trimer, when it is treated with sodium alkoxide or aryl oxide, the Cl is replaced by alkoxy group or aryl oxy group. When the same trimer is treated with sodium thiocyanate, so the Cl is replaced by thiocyanate group. Coming to the another property known as hydrolysis. So phosphonitrile chloride trimer on hydrolysis gives all the Cl are replaced by the OH and the compound becomes unstable. It undergoes isomeric change to form trimeta-imidophosphoric acid. Now, these are some of the points of phosphazenes. Now, let us take how the phosphazene can also be explained. This slide says phosphazenes are the class of chemical compounds in which phosphorus atom is covalently linked to a nitrogen atom by a double bond and to 3 other atoms or radicals by single bonds, while other substitutions produce relatively persistent compounds. In organic synthesis, in term largely refers to species with 3 amino substituents bound to phosphorus. The compounds are usually stable. Examples of the phosphorane class of molecules and have a remarkable proton affinity. As such, they are one of the eminent examples of neutral organic superbases. Two examples are hexachlorocyclotriphosphazine and bis triphenyl phosphine iminium chloride. Phosphazenes are also known as iminophosphoranes and phosphine imides. Yes, coming to this phosphazenes. The phosphazenes are cyclic or chain compounds that contain alternate phosphorus and nitrogen atoms with two substituents on each phosphorus atom. The three main structural types are cyclic trimer, cyclic tetramer, and the oligomer or high polymer. A few cyclic pentamer and hexamer are also known. The another way of explaining this phosphazene polymers. Phosphazenes can be polymerized. Their polymers have advantages over carbon-based polymers, polyolefins and polyesters. By varying the nature of the side chain are various elastomers, plastics, films and fibers have been obtained. They are flexible at low temperatures and water and fire resistant. Some R groups like the ethyl group are water repellent and do not interact with living cells and promise to be useful in fabrications of artificial blood vessels and prosthetic devices. That's why these phosphazene polymers, they are prepared like a tubes and introduced into the human bodies. Here I have shown how the polyphosphazenes can be synthesized. This synthesis I have already explained in the previous slides. So this is also the another synthetic, the way in which these things can be done. So this slide shows about the preparation of phosphazenes. This preparation also I have explained in my previous slides. Yes. Coming to the structure of phosphazenes. Now in this, phosphazenes basically contain phosphorus and nitrogen. If you see the electronic configuration of nitrogen, it is 2s2, 2p3, where 3 unpaired electrons are there in px, py and pz orbitals. If you take the phosphorus, the electronic configuration of phosphorus is 3s2, 3p3. But phosphorus is having the vacant d orbitals because it is in the third shell. Therefore, one of the electron from 3s, it shifts into 3d xz or the yz orbital. As a result, nitrogen atom undergoes sp2 hybridization and phosphorus atom undergoes sp3 hybridization. Among the three sp2 hybridized orbitals of nitrogen, one sp2 hybridized orbital of nitrogen contains the lone pairs of electron and other two sp2 hybridized orbitals, they involve in bonding between the two other phosphorus atoms through a sigma bond. Phosphorus atom undergoes sp3 hybridization and results 4 sp3 hybridized orbitals. out of the 4 sp3 hybridized orbitals, 2 orbitals are involved in the sigma bond formation of phosphorus and alkyl or aryl or chloro group. And other 2 are involved in the sigma bond formation between the 2 nitrogen atoms. After the formation of the sigma bond, there remains 2 unhybridized the orbitals. One is the pz orbital in nitrogen, another is dyz or dxz orbital of phosphorus, and these 2 unhybridized p orbitals, they overlap laterally and forms d pi p pi bond between nitrogen and phosphorus. This is a unique character, that is a double bond in case of phosphazene it is a d pi p pi bond. Because since nitrogen atom is sp2 hybridized, phosphorus atom is sp3 hybridized, so therefore whole this molecule is not a planar molecule. That's why in this slide the last sentence says all phosphazenes are not planar. So whatever I have said, the same thing is written in this form. The halide trimers consist of a planar 6-membered rings. The bond angles are consistent with sp2 hybridization of the nitrogen and approximately sp3 hybridization of the phosphorus. 2 of the sp2 hybrid orbitals of nitrogen containing 1 electron each are used for the sigma bonding, and the third contains a lone pair of electrons. This leaves 1 electron for the unhybridized pz orbital. The 4 sp3 hybrid orbital of phosphorus are used for sigma bonding, leaving a 5th electron to occupy a d orbital, maybe in the dyz or dxz orbital. Why it is yz or xz? Because the p orbital is in pz orbital. All phosphazenes are not planar. The dxz orbital of phosphorus atom overlaps with pz orbital of the nitrogen atom adjacent to it. The dyz orbital, which is perpendicular to the dxz, can also overlap with the pz orbital of nitrogen. There may be in plane pi bonding between the sp2 non-bonding orbital of nitrogen and the dxy and for dx square minus y square orbital of phosphorus. So these are some of the important points regarding the structure of phosphazenes. In phosphazene, that is the phosphonitrile chloride, the bond angle between NPN is 118.4 degree and the bond angle between PNP is 121.4 degree. Similarly, the bond angle CLP-Cl is 102 degree. The bond length between N and P in a ring is 158 picometer and the the length between P and Cl is 197 picometer. So based on this, the structure of phosphonitrile chloride trimer is shown in this slide, which is also having the resonating structures. So here I have shown how the orbital overlapping will be there in phosphonitrile chlorides. and also have said about the inorganic polymer or the inorganic rubber. The inorganic rubber is a linear the phosphazene, that is phosphonitrile chloride. Coming to the properties of these phosphazenes or the phosphonitrile chlorides. The phosphazenes are highly thermally and chemically stable. They are all water repellent. They are used for low temperature lubrication. LMW silicone polymers are soluble in organic solvents. These are good insulators. Phosphazenes resistant to oxidation. They have non-sticking and anti-foaming properties. Coming to the applications of phosphazenes. Phosphazenes are used as greases, varnishes, and lubricants. They are used for waterproofing in electrical condensers. They are also used for various purposes at low temperatures. Phosphazenes are used in medicinal and cosmetic implants because of low toxicity. These are used for high temperature oil baths, high vacuum pumps, etc. Other applications. The halides of phosphazenes are used as rigid plastics, expanded foam, and fabrics. These are used as water and fireproof materials. The phosphonitrile chlorides are unaffected by oil, petrol, and other solvents. These are also used as catalysts in the manufacture of silicones. These are used as flexible plastics. Apart from this, the many other uses we come across. This slide also gives almost the same informations what I have said in the earlier. Students, go through these phosphazenes and try to learn about these. These have very wide applications. Thank you.